Hello everyone and welcome to the OneClass channel. My name is Donna Riel and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now we're just going to get started on our set of questions for today's session. Okay, so question 1 asks, a disproportionation reaction involves a substance that acts as both an oxidizing and a reducing agent, producing a higher and lower oxidation states of the same element in the products. Which of the following disproportionation reactions are spontaneous under standard conditions? Calculate delta G and K at 25 degrees Celsius for those reactions that are spontaneous under standard conditions. So they have A and B, which I think are just examples of disproportionation reactions, and we are going to be looking at C. So I'm just going to write the unbalanced reaction down, and then I'll also show all the steps on how we would balance this. So we start off with chlorous acid, and then this forms chlorate, which is ClO3 minus, plus hypochlorous acid, so this is HClO aqueous. Okay, so this is our unbalanced reaction. So the first step in balancing redox reactions is to write the two half reactions. So the reduction reaction and the oxidation reaction. So we're just going to break this unbalanced reaction into two. So the first one, I'll write the oxidation reaction. Then this is H. So the chlorous acid making chlorate is the oxidation reaction. And then for the reduction, it is the chlorous acid making the hypochlorous acid. Okay, so step 2 is to balance all the atoms. So typically you want to balance all the hydrogens and the oxygens. And you also want to balance the charges. So I'll show how we would do that. Okay, so just rewriting oxidation and reduction. Okay, so let's look at the oxidation reaction first. You'll notice that there is a hydrogen on one hydrogen on the reactant side, 2 oxygens on the reactant side, and then 3 oxygens on the product side. So first, I'm just going to write like a box over here. We are going to add water to add oxygens. And then assuming this takes place in acidic conditions, we are going to add protons to add hydrogens. So we want to add the water first, since it contains hydrogens, and it'll just be easier to balance out if we add out the water first. Okay, so again, we need an oxygen on our reactant side. So I'm going to add water. So now the oxygens are balanced out, but our reactants has 2 hydrogens, or 3 hydrogens, sorry, and our products has none. So now we can add H plus to balance the hydrogens out. So we need 3 H plus ions. And now we want to make sure that the charges are balanced as well. So on our reactant side, all the charges are neutral, there are no charges. And for the products, we have a single negative charge and we have 3 positive charges. So therefore, to neutralize the positive charges, we need to add 2 electrons. Okay, so let's do something similar to our reduction reaction. We start off with the chlorous acid, and you'll notice that for this, there's 1 extra oxygen in our reactant side. So I'm going to add water to my product side. So now there are 3 hydrogens on my products, so I need to add 2 protons to my reactants. And then to balance out this positive charge, I need to add 2 electrons as well. Okay, so now everything should be balanced in terms of atoms and in terms of charges. So the third step is just to combine both of the half reactions. So when we combine the half reactions, we want to then also cancel out anything that is the same on both sides. So I'm just going to combine them. So we have water, and we also have 2 moles of chlorous acid in total, 2 protons and 2 electrons. And then for our product side, we have the chlorate ion plus 3 protons plus 2 electrons plus hypochlorous acid plus water. Okay, so I'm going to cancel out the water since it's just the same on both sides. There are 2 protons on the left and 3 on the right. So I'm going to cancel this whole thing, and we're left with 1 proton on the right. The electrons cancel out as well. And then our final balanced, net balanced equation is the following. Yep, so now we have our net balanced reaction. So step 4 is to find the overall reduction potential. So this can be expressed as E cell is equal to E cathode plus E anode. So this is given in the question. So for the cathode, it is 1.21. So that is our reduction reaction. And then for the anode, it is going to be negative 1.65. Oh wait, actually it's the other way around. So in the cathode, it's 1.65. And then the anode is negative 1.21. And then this is in volts. And then we have an E cell of 0.44 volts. So this means it is a spontaneous reaction. So I'm just going to start a new page because this is a long question. But basically step 6 is to now calculate for delta G. So delta G is equal to negative N times F, and then the potential, which we calculated in the previous step. So N is the number of electrons transferred. So if we look at our net balanced equation, there were 2 electrons that were transferred. F is Faraday's constant, and its value is 96,485.33 coulombs per mole. And then our potential is 0.44 volts. Okay, so multiplying this out, we end up getting negative 84,907 joules. So the reason why we have joules as our units now is because joules is equal to volts times coulombs. So now we can just express it as joules, and then this is per mole. Okay, so now step 7 is to find K. So we can find K using the equation delta G is equal to RT ln K. So now let's rearrange this equation to solve for K. So it's going to be ln K is equal to negative delta G over RT. So R is just a constant. I'll write it out below, but the delta G is just what we solved in the previous step, negative 84,907 joules per mole. And for our R, it is 8.314 joules over moles times Kelvin. So this is usually given in the question. And the temperature is 25 degrees Celsius, but we want it in Kelvin. So it is 298 Kelvin. Okay, so this whole value here is equal to 34.27. So now, and I'll just rewrite it here. So ln k is equal to 34.27. And then in order to isolate to solve for our k, we need to get rid of the ln. And to do that, we base the e on both sides. So if you have a scientific calculator, you can just plug that in. And then you should get a k value of 7.6 times 10 to the 14. Okay, so long answer. But let's see what our junior tutor said. I'll start from page 1. So they wrote out, they showed that the anode, the chlorous acid is oxidized to chlorate, and at the cathode, the chlorous acid is reduced to hypochlorous acid. Balancing the charges to balance the charges, adding electrons to the more positive side or electrons efficient side, and to make the equal, multiplying both the equations by the lowest common factor among both the reactions. Yep, so I guess they already... Oh, it's because the half reactions were given already, right? Yep, so they just did the same thing. So they added both half reactions and got a net balanced reaction. The same as mine. We can find the reduction potential for the overall reaction by the equation E cell is equal to E cathode plus E anode. And they got 0.44 volts. As the value is positive, the above reaction is spontaneous. Then they found delta G. So I did that on this page. 2 times Faraday's constant times the potential of the cell, and they got negative 84,907 joules per mole. And then finding K by using the given relation, delta G equals RT times ln K. Okay, so they converted ln to the log, but either way works. Where R is 8.314 joules per mole Kelvin, T is 298, and they ended up getting 7.584 times 10 to the 14. Yep, so this solution is correct. Okay.